Okay, so welcome everybody to this SPD seminar. I'm very glad that you have joined, even though the weather is very nice here, at least in New York. So our speaker today is Markus Reiß from the Humboldt University in Berlin. Markus actually started his research career also at Humboldt University. So he did his PhD there in 2002, then spent a couple of years as a postdoc at the Weierstrass Institute of Analysis and Stochastics, before he was then appointed a professor at the University of Heidelberg. And finally, in 2008, he moved back to HU Berlin. And since then, he has been a full professor of mathematical statistics there. So Markus's research is mainly on statistics for random processes and non-parametric statistics. But recently, he has also started to work on statistical problems for SPDEs. And we're very happy to have you here today and hear about your latest work. So we look forward to your talk titled Non-Parametric Estimation for SPDEs via Localization.
Yeah, thank you very much, Carsten, for the invitation. And it's a great pleasure to speak to you. And it's, in a way, it's an advantage of the current crisis that it's so simple to give a talk at Columbia. Actually, I did something like SPDEs during my PhD, where I did statistics for stochastic delay differential equations. So at that time, I digested everything from Daprat to Zapcik and so on already. So, but I turned to SPDEs about 5 years ago. And you see here, we now have a CRC, means Collaborative Research Center. So it's a big research tanker, which is called data assimilation, which is really about stochastic processes and statistics. And I have a joint project there on statistics for SPDE. So I really got interested into that subject. And what I want to present today, I chose the title more or less of one of the papers, Non-Parametric Estimation for SPDEs via Localization. But my aim is more to give you an overview, to point out or at least I try to transfer a little bit the ideas and a little bit the interest. Also, on one hand, from the mathematical perspective, there are nice challenges, I think, for SPDE theory people, but also the kind of applications. And I think the field of SPDEs is now sufficiently mature to go away also to other disciplines and try to convince them that this is a good idea to look at or to model with SPDEs. Okay, please interrupt me whenever you don't understand anything. Just speak up. I might not check any chat or whatever. But of course, at the end, you can also put questions into the chat or yeah. So let me start. This is the most complicated slide. Actually, I copied this from this paper by Till Brettschneider and colleagues from Warwick. And it's about cells, or better, amoebae. So it's about cell motility, so movement of cells. And here you have such a cell, okay? And with some markers, you see some actin. So let's say some activity here at this line or part of the cell, because there's some signal coming from there. So usually, people would put sugar there, some nutrition, and the cell would like to move there, okay? And here they do it with some shear stress, some physical forcing, but it's somewhat the same situation. And what they want to understand is now they change the signal. So instead of putting the sugar on top, they put it here to the bottom, and you see slowly this actin suddenly turns up here at this border of the cell, okay, and it moves down. And this kind of repolarization is not really understood. And I think it's it looks like a nice question, but I didn't think that it's so interesting when I first saw this. But then I really saw pictures. I can, if you like, at the after the talk, I can show you videos also of these cells moving around. They really move around like a planar Brownian motion. If you see under a microscope, you take a video, it really looks like a stochastic process. And what you then see is up here, you need not recognize what it is, but there are 3 different models the physicists look at. And these are all kind of systems of PDEs, okay? And what these people did here in the paper is they really took the measurements here. Here you see the same measurements. So along the x-axis you have time, and here you have the circumference of the cell, okay? And you see where the activation is at which places. This here is for one cell, and this is the average over 18 cells, I guess. And you see this kind of, changing polarization. First, it's here at this part, and then it moves over there. And they want to model this, and they want to understand at this kind of mesoscopic scale, how does it work? What kind of physical models would really be able to produce this kind of behavior? So they understand quite well what is inside one cell, what happens, what is the signaling there, and so on. But this kind of interplay between clumps of cells in amoebae, they just don't understand, okay? And what these people did is they took this deterministic PDE model and just assumed they have measurement noise and did some kind of, let's say, curve fitting algorithm, which is more or less least squares algorithm, assuming you just have Gaussian measurement errors or something. So you have deterministic dynamics and Gaussian measurement errors. And we were really not satisfied, because if you look at these cells, they really move in a very random walk fashion, yeah? And so we took this up. There's now a joint preprint. And again, you need not look at this in all detail, but we took up the easiest model, which is the Meinhardt model, which is exactly the model that you would have here, and we added some noise, okay? Now we are in the SPDE framework. So this is what is called an activator inhibitor model. So you have two states, or two reactants, A and I, and X is just the vector. And the time evolution is just giving here by some diffusivity for A and I, some nonlinearity, some reaction term. And in our case, it could be a little bit more space-dependent noise levels, but more or less space-time white noise here. Okay, and I just wrote down for you how the nonlinearities look like from the physicist perspective. I mean, if you like to look at it, it's a little bit, these are kind of a rational function. It's going to be bounded, C infinity. So at least you could try to think. So there will always be a solution, at least in a distributional or weak sense. Okay, so but you have to think about this. So this is kind of a first model for this kind of physical phenomenon. And what they did is, or what they can really see under their microscopes, is this activator. This is this actin concentration where they have markers and they can see that. They don't see this I here. And what they see more or less, of course, everything is discrete, but they have a good resolution in time, on a time interval. But only in the preceding picture, it was 20 spots or localizations in space where they observe it. And what they ask you then, or I mean, what they ask themselves without this white noise part is then how large, how big are all these parameters, which all have some physical meaning, okay? And in particular, I asked them, what are they most interested in? Most interesting for them is this diffusion parameter here, dA, okay? So this is, let's say, the framework, and then you can look at it and again try to be convinced. So I really try to convince you that SPDEs are also cool from a more aesthetical perspective. Of course, it's mathematically great and challenging, but here, this is real data. Okay, so this is this kind of actin concentration. Think of a torus here, and this is space, and in this x-axis is time, and this is even an average. So it's already kind of averaged over 18 cells of this actin concentration. It looks like a, some solution to an SPDE. Yeah. Here, this is what the physicist would say in a Meinhardt model, how this should look like. So they can rebuild. This was a big work in pattern formation by Meinhardt, that they can have a two-state PDE model where they really have this repolarization. Okay, first activity is here, and then it's in the middle. And this is here one SPDE realization where you just add a little bit of noise. Okay, the noise level is small, but already there are certain facts appearing. So there are many pure probabilistic questions there. For instance, what we noticed, but we could not prove, is that this repolarization starts earlier if you add noise, space-time white noise. Okay, so in a way, for the physicists, it's interesting. So the pattern formation is even faster. So noise creates structure instead of destroying it. Yeah, so this was kind of interesting, but this is more an experimental observation, of numerical experimental observation. Okay, I have a video. I know it's probably not good to see for you, but I'm a mathematician, and in the end, I'm a pure math guy. So this was just kind of to raise some interest, and I'll come back to this physics example later. But let's first think of the easiest thing that everybody in SPDEs knows too well, probably. It's just stochastic heat equation, okay? So W dot is just space-time white noise. Here you have Laplace operator on some bounded domain in dimension D, and here you have a vector theta, okay? And the idea here was, I don't know whether you can see this, but you do this for two different thetas. Here's a small diffusivity, and here's a larger diffusivity. And what I like about these pictures is just a little bit to relax also for you, is that if you see these pictures and I ask you, what is theta? Even if you think about it like a physicist, perhaps you do not come up with an immediate solution. So later you will see an estimator, and it's become more or less clear why it's a good estimator. But I don't know whether you would have immediately an idea how to estimate theta from this or that data, okay? Or to have a mathematical procedure to say at the left theta is smaller and at the right it's larger or whatever, okay? Although you have a feeling from your eyes. Okay, so this is a little bit to tell you, even if you're in theory in SPDEs, I think they are kind of nice, easy questions to ask where the answer is not obvious. Okay, so this was kind of the teaser at the beginning for you. So we had these examples. I will start because I assume, or Carsten told me, that you are not so familiar with statistics. I make a crash course in statistics for stochastic ordinary differential equations, 3-4 slides. Then I will tell you something about standard approaches for estimation for SPDEs and how we overcome certain obstacles there. And then I will go to this kind of main part, nonparametric estimation for SPDEs. And then I'll conclude. Okay, let's go into math. So, I mean, I know that there are great guys at Columbia in finance. I don't know whether anybody is around now among the participants. So you know very, very well what is nowadays called volatility estimation, okay? So estimation of the diffusion coefficient. Let's assume here, which is in finance usually not the right model, that you really have a diffusion, a Markov process, and you want to estimate sigma of xt, dwt, okay? You have some drift here, one-dimensional. And this is just very basic, of course. You just look at you observe this guy here continuously over some time interval. What do you know about sigma? And of course, I mean, for you, it's probably might be trivial. You can just take the quadratic variation until time t, okay? And what you get out is the integral from 0 to t sigma squared xs ds. And this is differentiable in this case. And so you know sigma squared at xs is what you observe. And at all points that you really visited during this time interval 0 capital T, okay? You can introduce local time if you like. And so what you can say is, in this idealized world where I really see the whole trajectory in path space, in the space of continuous functions, I'm really, I have no problem just to identify the sigma here. For a probabilist, what does it mean that is identified? It just means, I mean, let's say up to this, wherever we visited, it's just meaning that if you have two diffusion processes with two different sigma functions here, or let's say constants, sigma 1 and sigma 2, they generate singular laws in path space, okay? The law of the observation in the space of continuous functions for different sigma are mutually singular, okay? And so this is, I guess, most of you know, but it's kind of intriguing that if you had continuous time observations, the sigma is not a problem. Of course, why do people work a lot in financial econometrics on that? You only have discrete observations, but usually you can have here these kind of high frequency asymptotics. Carsten is also a big expert in that. If the observation distances tend to 0, you can just, with some kernel function or whatever, you can approximate. Okay, so this helps you already, this theoretical result to clarify. Okay, so we summarize. So the sigma is more or less identified by continuous time observations. Perhaps I stop here for asking you whether you have questions for this kind of statistical concepts, or if not, I'll continue. But I know when I start speaking, I'm excited myself, and then you better interrupt me if it's too fast or too slow. Okay, next slide is of course the other parameter. So assume you have a drift. Let's assume it depends on some real parameter theta, and the same sigma. You know the Gazanov theorem. There's a density, which you can then say is likelihood, and which in other words means that certain regularity assumptions well understood. For different B's, the laws are mutually equivalent, okay, mutually absolutely continuous in path space. So you cannot identify the drift if you only observe one trajectory on a finite time interval, okay? And what do you do in statistics then? Of course, things change if you go into asymptotics. So if you let time tend to infinity, or you have n independent realizations of your trajectory, or you let the noise level tend to 0 or something like that, okay? Then things separate again. But the drift is not identified. These are kind of these standard, things you learn in statistics for continuous time stochastic processes. And just to have a very simple case study, which will be helpful for the stochastic heat equation in a minute, is you can look at the Ornstein-Uhlenbeck process, okay? Look at this Ornstein-Uhlenbeck process, evaluate the maximum likelihood estimator. So this is how it is defined, the maximum likelihood estimator, okay? You assume you observe really the trajectory, so you can form the stochastic integral here in the numerator and divide by this Lebesgue integral in the denominator. And believe me, this is just the maximum likelihood estimator for Ornstein-Uhlenbeck process. And this is what you do with the data, okay? And now, of course, you want to analyze it. And if you plug in the dxt that you have here, okay, you just replace it. You see, what does it actually do, this MLE? It gives you the correct value theta, which comes here from this part. You divide exactly by xt squared here in the integrand. And the second part here is just the martingale part divided by the integral over xt squared. Okay, and which is kind of, will come up later. It's quite nice structure. This is a stochastic integral. It's a martingale divided by its quadratic variation. Okay, up to the constant sigma. So this really helps you to do a lot of mathematics there. And in fact, what you can prove is now asymptotic theory. So assume, for instance, you're in the stationary regime, so theta is negative. And what I want to do is I also want to allow that theta may vary in the asymptotics, okay? And if theta becomes large, I can still look at this quotient of the estimator and the true theta and its difference to 1. And if I scale by t times, because theta is negative, absolute value of theta, this is asymptotically normal, okay, Gaussian. Whereas martingale central limit theorem is nothing very serious, but we'll see exactly this effect later. So you can estimate theta when it moves, when it becomes larger, even when t is fixed, okay? So there's something to be understood. But I'll come to that later. But this will be helpful to understand statistics for SPDEs. I'll point this out. Okay, But these are kind of basic things you can just find out in standard diffusion statistics, say. Okay, let's go to the first simplest, let's say, infinite dimensional Ornstein-Uhlenbeck process, to the stochastic heat equation, okay, we saw before. I just want to explain it there, and afterwards things become just more and more technical, and I will only present results. So here, let's try to understand this really more in detail. And so stochastic heat equation, Laplace operator, now we are on some bounded domain in RD with some boundary conditions. And we can perfectly live here with kind of weak solutions. Okay, so you need not to stay in dimension 1 or and there's a constant theta we're interested in. Here space-time white noise, and let's say sigma is also just a constant there. And what is the easiest idea to think about? And it really helps to look at easy cases where you can do so in order to understand many phenomena. This is, I just said, so I grew up in a way as a student with the Prat and Zapchik book. So what you do, you think of this as of this SPDE as an infinite dimensional SODE by just going into the spectral decomposition into the eigensystem. So lambda k eigenvalue, ek eigenvectors or eigenfunctions. So think of Fourier functions. And you know the lambda k's are negative and growing polynomially in k depending on the dimension. Okay, yeah, if the domain is smooth. And you just look at this. This is a scalar product now in L2 of D, okay, in space. And you just look at this at this one-dimensional process now. It's just a coefficient process. And this is then just given by this formula here. Here you just lambda k xk, because it's the eigenfunction, the ek, okay, you just get out this multiplicative structure. And these w dot k are just, I write it here like in the physicist notation, okay? So this is time derivative of x, and this is something like time derivative of a Brownian motion wk, of a scalar Brownian motion. Of course, you could write dxk of t and so on, and dwk of t. But because this is an orthonormal basis, these are independent Brownian motions that you have here. And so you decouple everything completely, and you just have an infinite sequence indexed by k of Ornstein-Uhlenbeck processes. So if you now ask how to estimate theta, if you observe everything perfectly, you have infinitely many Ornstein-Uhlenbeck processes where you do not estimate theta, but where you estimate theta times lambda k, okay? And then you divide by lambda k. So this is what you want to do. And now you see my remark already. It's going to appear on the next slide, but I'm interested in theta, but I have an Ornstein-Uhlenbeck process with theta times lambda k, and lambda k in modulus of lambda k tends to infinity when k becomes large, okay? So this factor in front is really driving back the Ornstein-Uhlenbeck process further and further, the higher you go into the frequency. Okay. And again, now you can look at a maximum likelihood estimator, then you divide by lambda k in addition, and you get exactly this kind of asymptotics as before, just by observing, let's say, one Fourier mode, and then you let you just assume times capital T times the lambda k, the kth eigenvalue tend to infinity. And what is now kind of structurally interesting, you can keep t fixed, so you have a fixed time interval, and you go in the frequency to infinity. You let k tend to infinity, then also the lambda k becomes arbitrarily large, and then you can estimate theta with a certain rate of convergence, which means if you have complete observation of in the whole path space, okay, which is now, of course, indexed by time and space, then you can even identify theta, okay? You can go to the limit yourself because you have all the Fourier modes at your disposal. And so this is kind of interesting. It's different from SODEs, okay? This is, for a statistician, this is kind of great. You need not infinitely many observations in the limit or time tending to infinity or small noise asymptotics. you just stay on a fixed time interval, and you can, by going in the frequency in the space, you doing asymptotics inside that, you get some identifiability. Okay. I hope this is what is called a spectral estimator. And this is a good point just to give you a very selective overview of the literature. So this approach, the spectral approach, was propagated by Hübner and Rosowski in '95. Yeah, so this is a highly cited paper on that. And has many papers afterwards looking at statistics for SPDEs used exactly this spectral method, the spectral estimator. There are papers by Ibragimov-Rasminsky and 3 papers looking at statistics for SPDEs in the small noise asymptotics, but this is, let's say, rather of mathematical interest. I love this paper by Chalenko and Glatholz. They apply this stochastic, the spectral estimator to stochastic Navier-Stokes, to a nonlinear equation, and show it still works if you go for the eigenvalues of the Laplace operator there, although you have lower order nonlinearities, okay? And, oh, wait a second. And then there's this book by Lotowski and Rosowski, who also explain the spectral estimator at some point. And if you want to get a more profound overview of what's there in statistics for SPDEs, there's a very nice survey paper by Igor Chalenko. And then in the last time, there have been many papers on statistics for SPDEs. So people from the statistics and from the SPDE community start looking at this. And they really like this. So Carsten has and in the same vein, Bimiga and Traps, they look at power variations and things like that in order to estimate that. And there are more and more papers on discrete observations. I took here just one paper, which I quite like. And we maintain, together with Igor Chalenko, we maintain a website where you find all the literature that we are aware of in the area. So just if you like, I can give you the slides, you can check this literature. Now, everything was nice, but we had a problem. Later on, we want to have an operator which does not depend on, where we don't know the eigenfunctions. More precisely, the eigenfunctions depend on the unknown, okay? I'll come to that. So why does it work that this spectral estimator, that going up in the frequency, in the K, the lambda Ks grow, why can I identify? My, let's say, physicist explanation of that one is, if you go up in the frequency, due to this Laplace operator, the signal, which is the theta, really enters into the signal, into the high Fourier modes more and more strongly, while the white noise in the SPDE is of the same level, okay? So the signal to noise ratio grows in the frequency. And if you're now a little bit used to time frequency analysis, you know the higher you go in the frequency, the better is your space resolution. Okay, so we thought about, could we define something in space? And this is exactly what is happening here. And this was our main idea. So let's go to that. What we assume here is, we don't want to assume this was completely absurd, of course, and mathematically we observe the whole realization of an SPDE. Okay, you will never have that in practice. So let's assume which is very practical. We have let's say, I write it here like we have a pointwise evaluation, but you can think of this as a test function here. So we have a trajectory x of t and small x, and we get a local average in space of this one around some point x0 in our domain, okay? And the delta should be something like the resolution level. So we think of this k delta function like a Dirac delta function or a Dirac sequence. So when delta tends to 0, this goes to the Dirac. And so we think of this one as having kind of support of size or of diameter delta around x0 here, okay? So we just get a local average of the true solution there. So first of all, this is very nice because this is, you only need a weak solution. You can see this as a convolution or as a scalar product. And we scale it somehow. So in order to do asymptotics, we now let the delta tend to 0. In order to do so, we'll later scale the delta to tend to 0 and get this k delta x from one fixed function k, okay? And what we then observe is exactly this x delta, okay? This local average in space. We only see the solution locally. And this satisfies this kind of equation where you get scalar Brownian motion here. And here you get something like the convolution of the Laplace of x with a k delta function at the point x0. Okay, you can write down what you have. And of course, you can also put this by partial integration, the Laplace operator, to the other side of the convolution. And now let's assume we observe what I called x delta before, and where you here see the derivative in a sense. And here you see the convolution of x with Laplace k delta. Okay, this is exactly the guy that you have here. And then if you think of abstract statistical theory, you get something which is almost the MLE, but we augment this information here, so we call it augmented maximum likelihood estimator. And it's just given, remember this thing from Onshent-Uhlenbeck process, it's just given as a fraction of a stochastic integral here, divided by a Lebesgue integral here. So what is this? This is, again, you see it up here, the formula, but this is a local observation, so the locally integrated observation of the SPDE and its increments. And this is the same guy, but taken with a Laplace, okay? And if you now just plug this formula in, you see this is exactly the guy we have here. The theta gets out and you get martingale divided by its quadratic variation up to the sigma, okay? So it's exactly the same structure. And now the funny thing is, now the asymptotics are different. Now we let the delta, the space resolution, become smaller and smaller, okay? So you really have a Dirac sequence. The k delta is like a Dirac sequence going to the Dirac in x0. And we have this very simple model, theta is just a real parameter. And we get a rate of convergence delta and an asymptotic normality here. Okay, so forgetting all the details, this is very astonishing and new and interesting already, is that from this kind of local, when data becomes smaller, k has compact support, it's really, you have a very local observation in space, but continuous in time. You can identify the theta already, okay? So the theta hat delta tends to theta is consistent estimator. You even have a rate of convergence and asymptotic normality. I don't want to bore you with a proof, but more or less this is a proof, okay? So I don't know whether it's boring for you, but as we saw before, the structure of the estimation error is really martingale divided by its quadratic variation. And then you just see how large the quadratic variation is in mean. Yeah, you take the expectation, you write V delta as a Laplace K delta. Here you take the semigroup of your heat equation, and there's just one approximation of this kind of integral where you integrate more or less the semigroup, and then you're done. Okay, the standard deviation is smaller than the expectation in the limit, and then you just apply standard central limit theorem for continuous time martingales, if you like. Okay, so it's a very simple idea and proof, and but I think it's quite fascinating that it really suffices in order to identify the theta. Think of my video. You need not to observe globally in space. You just need to observe it in one little spot. Okay. And perhaps there's an open problem. I know there are some specialists in the area around. So all this is very, very much distributional theory. You see martingales converge, and so you do some kind of free normalization by looking at the fraction. If you think about the volatility estimation, we had this object what we called quadratic variation, which really identified the sigma. Okay, and here, if I don't, so I was thinking about a pathwise concept, which is more or less distribution free, as you have in rough path analysis and so on. Is there, can I somehow say something about the limit of this estimator? What is the kind of probabilistic object that is really there that identifies the theta, okay, locally? Is there some quantity I can look at and it's just different for different theta? And I don't know. So I looked a little bit at this problem, but I did not come up with it. So if you have any suggestions.
So I have a idea. I mean, I think the theta influences the quadratic variation or of your sample path in space, right? So it's the variance, the factor in front of the quadratic variation. I think is it based on that principle, the estimator?
Yeah, I mean, you see, so here the theta, if you only look at this equation here, but this is only the kind of, here it's in the drift. And so I think it's something, I mean, in time, it's only, you don't have quadratic variation in time, do you? You have only 1/4 Höder or something for the stochastic heat equation.
Quartic variation.
But it's not quartic, okay? You see, if you think about it, it's a quadratic form here in X divided by a quadratic form. Okay, it's really, and from a Gaussian, everything is Gaussian, if you like. If you start with a deterministic initial condition, everything remains Gaussian. Everything should be hidden in the covariant structure. So you should have quadratic forms as estimators. So you don't have a fourth variation here, a 4-power variation or something. And it's this fraction. I mean, so you can see here, probably this is kind of just rescaling everything, renormalization term. And my interpretation is more or less, I mean, what would you do as a physicist? You want to estimate this drift in front of the Laplace. So you look at the Laplace yourself. I mean, this is a guy. So I think it's kind of a distributional derivative of the solution, but still, this is something different from quadratic variation or power variation. So yeah, so if we should discuss, but I'm really not yet convinced that there's an easy answer. So
okay, I have another question. So because you're showing that slide, so basically here you're assuming that in practice, when you have your process X, that you have two devices that can measure the same process. One is with the kernel K delta, and the other device measures with delta, so the Laplacian of the K delta.
Exactly.
Okay, good.
So you can argue. So I will make just a short remark at the end. So in our paper, we also have the case where we don't have this observation, okay, where we don't have that. And what we have there is what is called a Proxy Mle. And it's only based on the X delta, okay? And but you can show same rate of convergence, but it has a larger variance and it's more complicated. You need more assumptions on the kernel later and so on. So it's a little bit more involved. And the proof is much more involved. So what I like is you need four-moment theorem. So people might like Stein-Mayer-Vin method or whatever, things like that appear here in order to prove a central limit theorem. And here it's particularly nice. So if you have the two, it's easier. And you can do this. What we do in practice is we discretize Laplace. Okay, if you observe at some locations in the neighborhood, you just take the discrete Laplacian. So we really used it for the experimental data. So it kind of works. Okay, and now comes the kind of message, perhaps. What we were interested in, we said, okay, we don't know how to apply this kind of spectral approach, is assume the diffusivity depends on space. So you have a theta of X here, okay? And if you're thinking physically about it, it should be between the two derivatives right in the middle, okay? So this is what you would call diffusivity from a physicist's perspective, or whatever heat conduction factor, and it depends on X. So think of a material with different heat conduction, so different materials along a bar or in your area of interest. And we want to estimate theta of x, okay? Now you have this, what I call Laplace sub theta operator, and the eigenfunctions will depend on this theta of x in a completely arbitrary fashion almost, okay? So if you don't know theta, you cannot apply the spectral approach. It's just not feasible because the eigenfunctions are unknown. Okay, if it was just theta times Laplace, the eigenfunctions would always be the same, just the eigenvalues differ. But here the eigenfunctions are not known and spectral approach is just not feasible. You could pre-estimate, but this makes life complicated, and I'm pretty sure it will not work in practice. Okay, and I'll go over this. And now the story is, of course, we started with this problem and came to the idea of this augmented MLE and these local observations. And the idea is now we apply exactly the same estimator. We do not change anything there and just hope that this same estimator, what we call augmented MLE, estimates theta at this point x0 because it only depends on the local observations. Of course, a PDE or parabolic PDE due to diffusivity, so everything is smeared out, okay? So there's the solution at x0 does depend on theta on all the domain, okay? So there's influence from everywhere, but still we hope that kind of the most influential part is from theta at x0, okay? So if the theta really depends on x. And what we can prove, you will see it a little bit more in detail the next slide, is we have the same kind of standard deviation or square root of variance term that we have seen before in the situation where theta is just constant. But we have an additional bias where we can really give you the form here. And here you see this is theta at x0 and theta at x0 plus delta times argument. So you integrate here over y or whatever. I didn't want to make the formula longer. And here you get the derivative on or gradient of k at y dy. And you see if theta is constant, this is just 0. And if theta is, you need to assume it more or less by definition. If theta is Lipschitz, this is here of the order delta. And if you're even, so the bias is of order delta. And if you're even symmetric here, you can even get this bias part to be of order small op of delta. And whatever the take-home message from this slide is just here, theta hat delta really estimates non-parametrically theta at x0 with a rate delta in an OP notation. Okay, this is under very, very few conditions. I don't list it. Of course, here you see k must be differentiable, and we have some dimension problem where we have some in dimension 1. We have to assume a little bit more on k than in higher dimensions. But this is more or less it. And this is kind of the theorem for what we want to, from this kind of introduction. We go a little bit more general. We can show much more. Now assume here is in general, you have kind of a linear SPDE. You would here like to have a general generator of a whatever semi-group. We are really forced to look at something like second order differential operator. So we take this Laplace theta is now a function, but we add first and zero order terms, depending again space dependent, okay? And we can also have a space dependent volatility, sigma of x times white noise here. We take exactly the same estimator, just to make you aware of that. We just take here the Laplace, okay, not the A theta. We don't know all these kind of A, B, theta, sigma, we don't know it. We just take exactly the same estimator. And under very few conditions, we can show again that with the rate delta, we get some asymptotic normality of the estimator. So it's completely robust, okay? You need not know the A or B, and you still estimate the theta. This is a great thing about diffusivity. So this is what you would know probably also from PDE theory. The symbol of the differential operator, more or less gives all the main properties. And here it's really on a kind of statistical perspective, which is great for applications if you think about it. You can really estimate the diffusivity without having to specify or to care, at least asymptotically, about lower order terms here in the first order differential operator or zero order differential operator. And you need not know the noise level either. Okay, so it's a very, very nice estimator. Okay, so there's some more remarks perhaps are in order. So, okay, it's robust to all this. What is new from a quite conceptual perspective? I don't know. I mean, you know, probably some of you know some colleagues in Berlin. So we have a strong theory in SPDE group in Berlin. And if I ask them, you have stochastic heat equation with this space-dependent diffusivity for different functions theta, do they produce equivalent, so absolutely continuous, equivalent, or singular laws in path space? The first answer would be, I don't know, I have to think about it. And then, of course, after some time, they get some ideas, but I think it's not trivial that if you have different functions theta of x, you can really identify them as a statistician. If you had complete observation in path space, which means probabilistically that you really get singular laws, okay, in path space for different functions theta of x. They can coincide on some parts of the space domain, but if they differ somewhere, you can identify them. Even if you only look at the, not the whole domain, but you only have the law in some neighborhood where they differ, okay, even locally. If you have, like in the example at the beginning, if you have different locations xi, so we now fixed one x0 and did everything locally around this. Now we can have different xi and we can do it there. Okay, this works exactly the same. We have a central limit theorem, so we can use Gaussian quantiles and define confidence intervals. And the last thing is, if you were a statistics audience, I would go further into that. We can show that this rate of convergence delta, which is kind of intriguing, where does it come from? Okay, this kind of spatial resolution really gives you the convergence rate of the estimator. We can show this is minimax optimal for any estimator. So this means whatever estimation procedure you take, you will never have a faster rate of convergence, at least. Not speaking about constants there, it's more tricky, but the rate of convergence is really optimal. And this is about bounding Gaussian covariance operators of this SPDE in some Hilbert-Schmidt norm, so Hellinger distance and then Hilbert-Schmidt norm of the covariance operators, these ideas. So it's kind of probabilistic work. The idea of the proof now for the theorem is there's a big scaling trick where you take the time interval longer and also the domain larger. So the domain becomes larger and larger and becomes in the end the RD, okay? You're on the whole real line. And by doing this rescaling, things work out quite nicely, and these lower order terms in the differential operator play less and less of a role, okay? And then you need very precise heat kernel and semi-group bounds, and we had to prove something on, for instance, the semi-group on these growing domains. We need uniform control of tail bounds there, and we use Feynman cuts because it was really nowhere in the literature. And then in the end, you apply again a martingale central limit theorem. Okay, so it's okay. One slide on nonlinear SPDEs. This is not my work. This work by Randolph Altmaier, Igor Chalenko, and Gregor Paseman from last year. These are two specific examples. I have a more general theory on semilinear SPDEs, but think of this stochastic heat equation now with a nonlinear reaction term here, F, okay? And if F is bounded in C infinity, or F is polynomial with the largest coefficient negative, and if you have a certain regularity here of the solution, X, to this equation, so there must be a solution and it should be in WSP, so Sobolev space of smoothness S in LP, and S is larger than D over P. And you can get this by taking here colored noise, okay? B is now some operator that could smooth here the white noise. Or if you take stochastic Burger's equation, again, with a kind of smoothing operation here, and just one concrete case is you take Laplace to the minus gamma for some gamma larger than 1/4, so something like at least 1/2 times more differentiable. Then the same message remains. So the same estimator, this augmented MLE, estimates this theta again exactly with the same asymptotics as in the linear case. Okay, so this means the nonlinearity does not spoil this estimation of this diffusivity. And the nice thing is, I think many of you know this kind of tool splitting technique. You look at the linear equation x bar, yeah, so you forget about the f, and you define x tilde as the nonlinear part, so x minus x bar. And then what I like very much, I want to, to highlight this for you, because I know if you're in SPDEs, you're very happy if you can have these kind of smoothness results, okay? But it's kind of an intellectual challenge to see how smooth the solution is in whatever fractional Sobolev spaces. But here it really helps for the estimator, because later we have this kind of convolution, or let's say scalar product of x with k delta. And so we just look at the nonlinear part here. And if x tilde has some smoothness, I can just apply here, whatever, generalized duality. You just get the W minus SQ norm, P and Q conjugate of the k delta of this Dirac sequence, okay? And if k has vanishing moments and so on, this will become smaller and smaller in terms of the delta, okay? So this becomes really small if x, or if the S here is large, okay? And based on these ideas, you can really show that this nonlinear part does not spoil the asymptotics of the estimator. And so I like it because they tried to develop a very general theory, but they had to have some extra, estimates for Berger's equation. It was not coming out of the general theory. So there's still something to be done on regularity theory with some statistical impact. Okay, I think I should come to an end with this, going back to the beginning, perhaps, with these kind of pictures. So for instance, let me just look here at the blue curves first. So this blue curve here, so this is, you see here the error in a log-log plot, the error of the estimator from Monte Carlo, and here's the delta. So when delta goes to 0, the error goes to 0, or the log error goes to minus infinity. And if you look at the blue curve, you just see this one. This is a linear estimate, the linear equation, and you apply the estimator, and it really goes linearly down, as you would expect. And if you have a nonlinearity, as we had seen there, you see it's first larger, and then asymptotically the error is like, so when the delta becomes smaller and smaller, the nonlinearity really does not spoil the estimator any longer. Okay, here you are almost as good as here. And this is here for the capital M is for 5 space observations, so at x1 up to x5. And here the red one is where you have them at a distance of the order 1 over delta. Okay, you get, if you make delta smaller and smaller because you have disjoint support of these kernels, or you want to have that, you get more and more observations. Okay, think of this kind of asymptotics. Then the same picture with some kind of wiggles is there. The linear estimator has smaller error, but in the end, even if you have a nonlinearity, it does not really spoil it. And this is done for the nonlinearity from the physicist model. And in this paper, we really used their data and estimate this diffusion coefficient dA. And here you get, I don't give you the physical measures, units, I forgot, but you get out something with a confidence interval, 95%, which has physical meaning. So this is really what the physicist says, yeah, this is the right order, this is okay. And it's very robust for different cell data. So we have, for different cells, the same experimental data. And this is kind of, in a way, convincing that you get more or less the same values for that. This is not really telling us, so the physicist would like to know much more, but this is at least the first go where you can really provide some values. Okay, let me close just with kind of pointing out. And so I hope that you had some, got some ideas, statistical ideas from the talk. What I think from this conceptual perspective is nice is that you have this identifiability in a finite time of this theta, of the diffusivity, which is completely different to the SODE case, okay? Then we had this idea of local measurements with this kind of space resolution delta, the augmented MLE. The optimal convergence rate was also delta, this robustness to linear or nonlinear lower order terms, and this kind of application, which I really like. And if you like, I can show you videos of Brownian motion, yeah, but it's live. It's not some molecules. And what we did is, this was Carsten's questions, more or less. We have an approximate MLE when this Laplace X delta is not observable. We think about multiplicative noise. Also in this application, it looks more like multiplicative noise. If you look at it, not additive noise, there are still some mathematical problems. So this is more or less, yeah, we have to bound some big variances, covariances of a nonlinear SPDE, which is kind of hard. What I would like to do for applications is, these guys, these physicists, came around with some PDE model and assumed they have some measurement noise. Of course, they have microscopes, cameras, they have some noise, but it's rather small. But can you distinguish PDE and SPDE models given some noise? So if you want to have a paper in Nature, you should provide a p-value on that one, okay? Somebody says, why do you use an SPDE model? Perhaps a PDE model would have been as good. And so you have to convince people by some really nice testing procedure. And what we are now aiming for at the moment very much is estimating of lower order coefficients. So first order differential operator coefficients, zero order transport reaction terms in the nonlinearity. How fast can we estimate them? It's clear we cannot estimate them as fast. So the rate of convergence really depends on that. For some cases in small dimensions, it's only identifiable if the time tends to infinity in dimension 1 and 2. And in dimension 3, it's already for infinite time identifiable. And we're also thinking about that the diffusivity tends to 0, which is very much the case in applications, that people are really interested in these nonlinearities or lower order differential operator properties, and the diffusivity is rather small. So what happens if the diffusivity tends to 0? So of course, again, the SPDE becomes less and less regular, okay, becomes rougher and rougher. But this is very, very good for statistics, because the rougher it is, the better the parameter to estimate is to estimate. Okay, with this, I really want to conclude, and thank you very much for your attention.
Thank you, Markus, for the very nice talk. Are there still questions? I have a question. So do you have an idea how to distinguish PDE with noise, observation noise, and SPDEs, and a true SPDE? Do you have an idea?
Yeah. So of course, so there's one thing. So if you talk to the physicists, especially if you look at an SPDE with additive noise and a PDE where your measurements have additional observational noise, okay? Mm-hmm. They don't understand, first they don't understand the difference. They mix it up. They say it's additive noise, okay? And so you really have to tell them that there's something happening. And what we did, so this is just for communication with other disciplines. So if you go back to this very first thing here, in this paper here, where we looked really at these data and so on, what we could show, and which was really interesting for them, is that this time to repolarization, so we defined it somehow that this kind of, the activity starts to appear in the middle. It really is earlier if you have just additive white noise in the SPDE. Okay, I mean, if you imagine this is the PDE solution, and you just add noise on top of it as on every pixel. Okay, of course the activity will not go to the left or whatever. It will remain. The average activity will remain after time 60, 70, whatever, to be in the middle. Okay, but if you add here a little bit more noise, it becomes earlier and earlier. So you really have a dynamical effect of additive noise in the SPDE, and we call it dynamic noise. Okay, so this physicists often understand. If you say this is dynamic noise, it really enters the dynamics. Now, concerning your question, is of course you are the right man to do that. Our idea would be to test an SPDE where the sigma, for instance, how we called it, so the covariance factor in front of the additive noise, it's 0 versus it's larger than something. Okay, I mean you could think of it's 0 or 1. And this means that you would have to look exactly at this kind of volatility that you're looking at, but with the additional feature that you have additional measurement noise.
Okay.
And this looks a little bit like this microstructure noise approaches in finance. Okay, this is exactly the same idea. You have some stochastic process, observed in noise, and you want to estimate its quadratic variation. So this is so. Probably. So we want to start this, and I'm happy to collaborate if you want to.
So
not yet done. We have not yet started, but I think I will approach you rather sooner than later to tackle this, because it's.
So I actually maybe I should stop the recording first, because I think we are the only one left here.
Okay. Yeah. It's true.